Spatial interpolation. Objectives. In this chapter, we will discuss about spatial interpolation, elements of spatial interpolation, types of spatial interpolation, that is global methods and local methods, comparison between spatial methods, GIS application of spatial interpolation. Spatial interpolation is a process of using point with known values to estimate values at other points. Through spatial interpolation, we can estimate the precipitation value with a location with no recorded data by using known precipitation readings at nearby weather station. In GIS application, spatial interpolation is typically applied to a raster with estimates made for all cells. Spatial interpolation is there for means of creating surface data from sample points so that the surface data can be used for analysis and modeling. There are two different types of surface is present. One which we are familiar with, that is a terrain, whereas the other one is not having a physical form but can be visualized in the same way as a land surface. Cartographers call this type of surface as the statistical surface. Example of statistical surface includes precipitation, snow accumulation, water table and population density. Elements of spatial interpolation. There are two basic inputs that are needed to find spatial interpolation. They are known points and interpolation method. The known points distinguishes the spatial interpolation from the isoplete map, which uses assigned points such as polygon centroids for interpolation. Control points. These are also called as known points or simple points or observations. These control points are points with known values and provide data necessary for developing and interpolate are the spatial interpolation. The accuracy of spatial interpolation is greatly influenced by the number and distribution of the control points. A basic assumption in spatial interpolation is that the values to be estimated at a point is more influenced by nearby known points than those of far. As a study area often contains data poor areas, the effective estimation of the control points may not be well distributed within the study area. The data poor areas can cause problems for spatial interpolation. Types of spatial interpolation. There are different methods to categorize the spatial interpolation. One such method is used to group spatial interpolation methods into global and local methods. A global interpolation method uses every known point available to estimate an unknown value. The local interpolation method, on the other hand, uses simple of known points to estimate an unknown value, because the difference between the two groups lies in the number of control points used in estimation. One may view with a scale from global to local as a continuum. Conceptually, a global interpolation method is designed to capture general trend of surface, and a local interpolation method the local or short range variation. For many phenomena, it is more efficient to estimate the unknown value at a point using a local method than a global method. Faraway points have little influence on the estimated value. In such cases, they may even distort the estimated values. Local method is also preferred because it requires much less computation than a global level. Second method of grouping the spatial interpolation method is into exact and inexact interpolation. Exact interpolation predicts a value at a point location that is same as its known value. In other words, exact interpolation generates a surface that passes through the control points. In contrast, inexact interpolation or approximate interpolation predicts value at a point location that differs from its known value. Third method divides the spatial interpolation method into deterministic or stochastic method. a deterministic interpolation method provides no assessment of errors with predicted value. A stochastic interpolation method, on the other hand, considers the presence of some randomness in its variable and offer assessment of production errors with estimated variances. Global methods. Global methods include trend surface model and regression models. Trend surface models. An inexact interpolation method, trend surface analysis, approximate points with known values with a polynomial equation. The equation or the interpolate can then be used to estimate values at other points. Because the trend surface model is computed by least square method, the goodness of the fit of the model can be measured and tested. Also, the deviation or the residual between the tab served and the estimated values can be computed for each known point. The distribution of most natural phenomena is usually more complex than an inclined plane surface from the first order model. The higher order trend surface model are required to approximate more complex surfaces. A cubic or a third order model, for example, includes hills and valleys. A higher order trend surface model therefore requires more competition than a lower order model. A AGIS package may offer up to 12th order trend surface models. They are variations of trend surface analysis. Logistic trend surface analysis uses known points with binary data and produces of probability surface. Logical polynomial interpolation uses a simple of known files to estimate the unknown value of a cell. Local polynomial interpolation can be used for converting a triangulated irregular network, that is TIN model, to a digitally elevated model, that is DEM model, and deriving topographical measures from a digitally elevated model. Regression models. Regression model relates a dependent variable to a number of independent variables. A regression model can be used for estimation using the regression equation as an interpolate or for exploring the relationships between the dependent variable and the independent variable. Many regression models use non-spatial attributes and are not considered models for spatial interpolation, but exceptions can be made for regression models that the spatial variables such as distance to a river or location specific elevation. Local methods. Because local interpolation uses a sample or known points, it is important to know how to select a sample. The first issue in sampling is the number of points to be used in estimation. GIS packages typically let user specify the number of points or use a default number. One might assume that more points would result in more accurate estimate, but the validity of this assumption depends on the distribution of the known points relative to the cell to be estimated, the extent of the spatial autocorrelation and the quality of the data. More points usually trend to more generalized estimation and fewer points may actually produce more accurate estimations. After a number of points is determined, the next task is to search for those known points. A simple option is to use the closest known point to the points to be estimated, and alternative is a select more points within a circle, the size of which depends on the sample size. Some search options may incorporate a quadrant work octant requirement. Previously, quadrant requirement means selecting more points from each of the 4 quadrants around to be estimated, and octant requirement means using age sectors. Other search options may consider the directional component by using an ellipse with its major axis corresponding to the principal direction. Theisian polygons. Theisian polygons assume that any point within a polygon is closer to the polygon known point than any other points. Theisian polygons were originally proposed to estimate areal average of precipitation by making sure that any point within a polygon is closer to the polygon weather station than any other stations. Theisian polygon, also called as Voronoi polygons, are used in variety of applications, especially for surface area analysis of public facilities such as hospitals. Theisian polygons do not use and interpolate but require initial triangulation for connecting known points, because different ways of connecting points conform different set of triangles. Delineate triangulation, the same method for the constructing a triangular integrated network, is often used in preparing the Theisian polygons. Theisian polygons are smaller in area where points are closer together and larger areas where points are further apart. This size differentiation can be the basis for evaluating quality of public service. Large polygon means greater distance between the home location and the public service provider. The size differentiation can also be used for top purposes such as rating for a stage class with larger polygons belonging to older tree. Density estimation. Density estimation measures cell densities in raster by using a sample of known points. For example, if the points represent the centroid of the census tract values to present reported burglaries, then density estimation can produce a surface map showing high and low by burglary rates within a city. For some application, density estimation provides an alternative to point pattern analysis, which describes a pattern in terms of random, clustered and dispersed. They are simple and kernel density estimation methods. The simple method is accounting method, whereas the kernel method is based on a probability function and offers options in terms of how density estimation is made. To use a simple estimation method, we can place raster on a point distribution. Tablet points that fall within each cell sum of the point values and estimate the cell density by dividing total point value by the cell value. Kernel density estimation associates each more point with a kernel function for the purpose of estimation. Expressed as bivariate probability density function, kernel function looks like a bump, centrigate a known point and tapering off to 0 over a defined bandwidth or window area. Density value in the raster are expressed values rather than the probabilities. The kernel density estimation usually produces a smoother surface than the simple estimation method does. As a surface interpolation method, kernel density estimation has been applied to a wide variety of fields such as public health and natural hazards. Inverse distance weighted interpolation (IDW). Inverse distance weighted IDW interpolation is an exact method that enforces the condition, that is, estimated value of 5 point is influenced more by a nearby known points than those of a far away points. An important characteristics of IDW interpolation is that all predicted values are within the range of maximum and minimum values of the known points. Small common close those lines are typically of IDW interpolation. Kriging. Kriging is a geostatistical method for spatial interpolation. Kriging differs from other local interpolation methods because Kriging can assess the quality of prediction with estimated prediction errors. Originated in mining and geological engineering in the 1950s, Kriging has since been adopted in a wide variety of disciplines. In GIS, Kriging has also become a popular method for converting LiDAR point data into digitally elevated models. Kriging assumes that the spatial variation of an attribute such as changes in the grade within a poor body is neither totally random nor deterministic. Instead, the spatial variation may consist of three components, that is, especially correlated component representing the variation of the regionalized variable, a drift of structure representing a trend, and a random error term. The interpretation of these components has led to the development of different Kriging methods for the spatial interpolation. Several forms of Kriging interpolators exist: ordinary, universal, and simple, just to name few. This section will focus on ordinary Kriging or OK interpolation. This form of Kriging usually involves 4 steps: removing any spatial trend in the data if present, computing the experimental variogram y, which is a measure of spatial autocorrelation, defining an experimental variogram model that is best characterized the spatial autocorrelation in the data, interpolating the surface using the experimental variogram, adding the Kriged interpolated surface to the trend interpolated surface to produce the final output. Comparison of spatial interpolation methods. In GIS packages such as ArcGIS offers a large number of spatial interpolation methods using the same data but different model methods. We can expect to find different interpretation results. Cross-validation and validation are two common statistical techniques for comparing interpolation method. Although some studies have also suggested the importance of visual quality of generated surfaces, such as preservation of distinct spatial patterns and visual pleasantness and faithfulness. Cross-validation compares the interpolation methods by repeating these procedures for each interpolation method. Remove the known point from the data set. Use the remaining point to estimate the value of the point previously removed. Calculate the predicted error of the estimation with the known value. Common problems that occur in spatial interpolation. It is important to remember that there is no single interpolation method that can be applied to all the situations. Some are more exact and useful than others, but take longer to calculate. They all have advantages and disadvantages. In practice, selection of a particular interpolation method should depend upon the sample data, the type of surface to be generated, and the tolerance of estimation errors. Generally, a 3-step procedure is recommended. Evaluate the sample data. Do this to get an idea on how data is distributed in an area, as this may provide hints on which interpolation method to use. Apply an interpolation method which is most suitable to both the sample data and the study objectives. When you are in doubt, try several methods if available. Compare the results and find the best result, the most suitable method. This may look like time-consuming process at the beginning. However, as you can gain experience and knowledge of different interpolation methods, the time required for generating the most suitable surface will be greatly reduced. GIS application of spatial interpolation. Spatial interpolation is an important component of almost any GIS. While a basic bivariate method are common, implementation of multivariate tool is most restricted to the most advanced system because of the lack of data structure and supporting tools for multivariate and temporal data processing and analysis. In spite of recent spatial interpolation advances in the development of methods and algorithms, an exponential increase in computational power, spatial interpolation, especially for large and complex data sets, can still be an iterative, time-consuming task requiring an adequate knowledge of underlying methods and their implementation. Integration of spatial interpolation within a GIS. Depending on application, spatial interpolation can be performed at 3 levels of integration with a GIS. First, within a more general program or command. Second, as a specialized command, or third, while using linkage to specialized software. Interpolation integrated at a sub-command level can be found in many GIS application programs such as computation of slope and aspect, automated raster resampling, flow tracing, hydrological modeling, etc. Most simple and fast local interpolation such as IDW, bilinear or local polynomial methods are used in this case. The interpolation is fully automated, hidden from the user, and while it is sufficient for most applications, it can result in artifacts in surfaces if an improper method is implemented. Interpolations integrated at a command level serve as data transformation functions. A limited set of basic and some advanced methods have been integrated within GIS. Most often, the simpler versions of IDW, TIN, Kriging and spilines compromises in numerical efficiency, accuracy and robustness are common, and upgrades to improve modification of methods are slow, especially for commercial system. Therefore, it is necessary to evaluate the results carefully and, if possible, to use more than one independent interpolation procedure. Although interpolations performed by specialized software linked to a GIS provide the most advanced and flexible tools, a time-consuming import and export of data or inconvenient work in a different software environment might be necessary. This approach still can be preferable, especially when data are complex and high accuracy is required. The advanced surface and volume modeling system with strong interpolation capabilities often also provide some basic spatial data processing, analysis and graphical tools, thus evolving into a specialized GIS. Examples of applications to illustrate the properties of selected interpolation method as well as their typical GIS application, a few representative examples and corresponding references are presented. Data were processed by GRASS, ArcInfo and S+, and the illustration were created by SG3D or SG4D and NVIS visualization programs. Summary: we have discussed about data spatial interpolation methods which are relevant for GIS application. It is obvious that there has been substantial development over the past decades from the point of view of accuracy, multivariate framework, robustness, variety of application and the size of problem tackled. However, the conclusions outlined by Burrow are still valid. It is unwise to throw one's data into the first available interpolation technique without carefully considering how the result will be affected by the assumption inherited in the method. A good GIS should include a range of interpolation techniques that allow the user to choose the most appropriate method for the job at hand. Computers will take over large part of this non-trivial task, but many problems remain to be resolved.